Hello and welcome to this video tutorial where I'm going to show you how to walk around in Minecraft, how to create mobs or AI agents or little creatures or life, to be dramatic, in your, well, whatever kind of game that you want, including a Minecraft kind of style thing. Last video we looked at combining biomes using lerp, and we're going to use that function again, lerp, to make characters kind of like look at you when you want them to, and then once they're looking at you, you could then give them a bit of speed, a bit of movement, and they will move towards you. So you've got like a chasing behaviour. So I've already got one little mob working there, and we can clone him. Ooh, we can clone him because in a previous video I created a script to create blocks, and all I'm doing really is cloning the block that I'm looking at. There we go, so we can defend ourselves. There we are. And let's run between here. So this is the kind of creature we'll be making. Notice that the eyes are rotating, or rather the head is rotating, moving the eyes around to look at our position. So that's what I'm going to show you how to do to begin with, and then you can build to something slightly more complicated, but very simple still, like these two fellows here, which kind of look like Minecraft creepers that I've made. Right, let's get going. So let's make ourselves one of him. I'm going to show you the script straight away, just in case you want some quick answers for how to rotate a character to look at you. So I've got, in the update function, I've just made a function called look at me. You could put it straight in the update function if you want to. And then I've said two things, so it's just two lines of code. Firstly, we need a vector3 direction, and this is direction from your creature to the target, and in this case it's the player's position. Okay, so to find that direction we write a simple subtraction. We say the target position, so that's going to be a vector3. That's like, if I click on my target, my me is my first person player controller in the scene, and on its transform it's got a position which is in fact 3 variables stored in a vector3 object. So it'll be position.x, position.y, position.z. So that's a vector3 object. It's just a variable with three components, x, y, and z. So that's our target position minus another position, and that's just this transform's position. So this script is attached to, in this case, our Sphero, I've called him. Don't usually get round things in Minecraft, so I thought I'd go for something round, and I've just stuck 2 smaller spheres to his face so that we can see which direction he's looking in. So he's also got a transform with a position. So if we say my player's position minus its position, we get a vector that points from the player, from the creature to the player, to the target. So we store that in dir for direction. So a vector3 dir is just a vector that points towards the target. Then we can say this transform's rotation, so our Sphero objects, its rotation equals, and we could just say, and I've written it down here, this transform, so the Sphero objects transform, look at, and that's a rotation function, look at the target position's position. And then actually we can skip out all of this stuff. We don't even need to find the vector pointing towards a target. This lookat function calculates that vector and then calculates by what quaternion and what rotation to perform to look straight at the position. If I just run that, let's have a look at what happens. So let's go and find our Sphero object during the actual game, while we're running the game, and see if it's looking at us. So I can already see the eyes. I think you can too. It's looking straight at us. Just in case that's a coincidence, let's go around the other side and see if it's looking at us. Right, it's instantly looking at us. which is kind of creepy. And you can kind of see that it's following us very, very quickly. Now, if that's the kind of behavior you wanted from your creature, perfect. You could just use this, let's find my mouse again, you could just use this one line of code that Unity provides to instantly look at you. But that might not be what you're looking for. You might want it to slowly look at you. So this is where, let's just stop the program, this is where lerp comes in handy. So again, a lerp is basically drawing a line between 2 points, or it could be 2 rotations or 2 values, and then slowly moving along according to a number. And so I've got here a very tiny number, 0.018. So every time the update function runs, the update loop runs, we're slowly rotating by this amount. If we just put 1 in here, then we'd have the same kind of behavior as before. We'll just snap our rotation, our looking rotation, to wherever we're looking. So let's explain this quickly. And then I want to just kind of make this creature from scratch to show you. But if you're after quick answers, here we go. So the rotation of our character equals, and then we start another function, and we say quaternion.lerp. Now, a quaternion is a rotation in 3D space, and whereas where a position is stored as a vector 3 with an x, y, and z component, transforms in Unity, rotations in Unity, which are on the transform component, are stored not as vector 3s but as quaternions, which is a little complicated. You can convert them into having 3 components, an x rotation, a y rotation, and a z rotation. That is a vector 3, and they're called Euler angles. And we might use those. We might use those later on. I've used them for kind of the arm rotations on my mobs, my like creeper kind of things. Anyway, so we want quaternion.lerp, and what this quaternion function returns is a new quaternion, a new rotation, but we don't want to rotate straight to look at our player. So firstly, we want to lerp from our current rotation, which is a quaternion, so that's just this dot transforming rotation, to, this is the second parameter, to the perfect target rotation. And to find that quaternion, we're going to have now another function inside this parameter, and that's quaternion.lookRotation, and that will just return a quaternion, and it will calculate from a vector direction to the quaternion you need to turn in that, or to be pointed in that forward direction. So we calculate that, we find that direction using this vector 3 direction equals the target position minus our current position. That gives us a vector 3 pointing towards the target. Okay, and that just takes that one parameter. Final parameter in our lerp is how much we want to kind of rotate or move towards the final like target rotation. Okay, so it's just a function within a function. We're passing a function as a parameter. So that's what all that means. Right. Let's save that, and that'll work. Right, let's do things from scratch though. Oh, I just need to turn that off. So now we'll get a much slower movement. Let's just show that happening. So then we know what we're going to create. And I think once we've pointed a creature at our player, then all we have to do is say move forward in this direction, and it will start to chase us, which gives us some interesting behavior. Right, which is what I've done for the creeper. So now we can see we're not looking straight at the player, but we're slowly moving towards it, which gives it a much more lifelike behavior. Okay, right. Let's create our own from scratch. Right. So what we could do is just go to Game Object at the top menu there, 3D Object. Let's create a cube this time. This is kind of like a blocky version. Okay, there we go. Now we need to create some eyes. It's very important which side you put these eyes on. You want to have them facing along the z-axis in the positive direction. So if you look at your coordinate gizmo at the top here, the z direction is this way, so it's along the blue one in my colours. You can change these colours. I've kept them as their defaults. So we want to place the eyes over here. So if I just rotate around, we could just let's make smaller blocks. So I've selected my cube, but let's call him blockhead. That's what our mob's going to be called. Let's just drag him up here in the inspector so I can see him more easily. Whoops. There we go, right. Let's bring him towards us a little bit so we're not getting confused by Sphero. Right, so the Z position is actually pointing towards us. So what I could do is select our blockhead and then press Ctrl or Command D, and that's duplicated him. So now I've got another one, which is handy because it's in the same position, so I can make it a lot smaller by just saying 0.4. Yeah, that's about right. 0.4, 0.4, and now I've got a much smaller one, and I'm going to use that as an eye. And if I just drag him out slightly, he'll point out of his body. I need to move this way a little bit. Oh, he's not pointing out of the body yet. Blockhead. Now he's pointing out of the body. Another handy thing to do if you do fiddly things like this is to click on the square up here, and then you go into like a flat isometric view so you can see exactly where it is. Okay, let's go back in this direction, and then you can also line it up very nicely without the perspective kind of ruining things. In fact, yeah, no, I was going to say I'm going to make it slightly bigger. I'm going to keep it the same. Right, we want a new material, so we can make him go black, or should I make the eyes? I made them kind of a green colour, I don't know why. So let's say eye green, and then the albedo, we're going to select green. There we go, and then I want to drag that onto our eye. I can't quite see it. Oh, there he is. Right, eye green. Brilliant. Whoops. Try that again. There we go. Right. Now I'm going to select that blockhead, that mini blockhead, the eye. Duplicate that again with Command or Control D. And now I've got one exactly the same. I'm going to move him there and then just adjust both of them. Right, let's flatten it so we can see exactly where they are. Right, so we've got our little blockhead character. We might want a mouth actually. Let's have a little green mouth down here. Oh, that's kind of nice, I think. Right, a problem might be that these are just squares, or cubes that I've positioned together aren't actually together. If we move this head around, the mouth and the eyes are just going to stay where they are. So we want them to be attached in a simple way to our head. So the easiest way to do that is to get hold of our mouth and eyes and then drag them inside the blockhead, the main head. There we go. So now what we've done is made those game objects children to their parent object. So when we select the parent object, everything else, itself and its children get selected. So then when we move these around, we'll move that parent object around, its children move around as well. So now, if we start rotating this head and things like that, everything else will get moved around with it. Right. So far, so good. Now let's create what we came here for, some AI. So let's create a new C# script and call that block head AI. You can call it whatever you like. We'll open up that script, and then we're just going to script or code what we did, what I explained previously. So every update, we're going to say rotate head, something like that. Now we need to go and create that function down here. It just wants to be void because it doesn't return anything. Hopefully my code is big enough. For some reason it's not allowing me to get any bigger or smaller. What's going on? It's really weird. Anyway, hopefully it's big enough anyway. Rotate head. So in rotate head, what we want to say is this transforms rotation equals, that's going to be a new quaternion, and we just want to lerp. Actually, we'll use slurp this time. Slurp and lerp are very similar. Slurp is just a spherical interpolation, which is kind of what you want to use if you're in 3D space and you're dealing with rotations. So slurp, but it works in exactly the same way. We just want its current rotation, this transform rotation, and then we want to move to we want to find the rotation that's looking exactly at our target. So we need to use a new or another quaternion function, which is from to rotation. Is that right? No. Look rotation. So look rotation is, it creates the quaternion rotation with the specified forward direction. We don't need to worry about upward direction. It will assume it's a default up. So look rotation, and now we can put in here a vector 3, which we're going to have to make. So we'll just call it target pos, and we want that. No, we want to call that. Okay, target direction. It's really a direction. So I'll call that target direction. And the final and third parameter in this quaternion slurp or quaternion lerp you can use is a floating point, so it's an amount. It's basically the speed that you're rotating at. So let's just put 0.1 and f to make sure that it's a float and not a double, else you'll get an error if you've used a decimal. Right, so we haven't created our target direction, so this needs to be a vector 3. So vector 3 target direction equals, and we just need to do the target position minus our position, and that will give us a vector 3, or the vector that points towards our target. So we need target position, which we haven't got yet, so we're going to have to go and find that. That's a player's position minus this transform position. There we go. So now we just need a target position. So let's do that via the inspector. So we'll say public, so we can see it in the inspector, and it wants to be a transform. We'll just get hold of the transform. Or can I say position? Let's try this. But how would we know? No, we'll have to say transform. Let's say transform target position, and then here we don't want the transform, we want the position. So the position vector 3 that's attached to that, or is a component of the transform. Okay, so now we need to attach this script to our blockhead. I should have done that to begin with. There we go, we've attached him. So now if we're going to have a look at our blockhead in the inspector, yes, we've got our blockhead AI and we've got our target position, and that needs a transform. So if I go and grab my player, which is the me, I've called him me, and go back to blockhead, drag that transform. If I just drag the whole game object in there, Unity will know to get hold of the transform. And it just crashed. and we're up again. Okay, don't panic, we're okay. So it's got hold of my transform. So it's using the player position now in this target position dot position in the update cycle. So it finds the target direction that's pointing towards a player, and it uses that as this parameter in the look rotation. So that calculates for us a rotation which is the same as the direction that you're looking at this target, and we're going to slurp from our current rotation to that perfect rotation looking at our target. Okay, so that's attached and that should be running. Let's go and have a look. Our blockhead should look at us. I think it's using a slurp value which is a bit faster than the Sphero object, so it should find us a bit quicker, or look at us a bit more quickly, which it is doing, yes. That's brilliant. And I tell you what, the rotation looks a bit better when it's a block. It's a bit more obvious. Right. So now what we can do is let's move this. Let's move this guy forwards. So once he's rotated his head in the update function, we could then say chase target. So we need to go and make this. Again, it's going to be a void function because it doesn't return any value. And all we need to say, because we're rotating towards that target, we just need to say move forward. We could do two things. We could say once you're kind of looking at the player, then move forward. So turn first and then do it. Or you could just keep moving forward. I kind of like that method. So let's just do that. We'll just go forward all the time. So all we need to say is this transform translate. So that means move our position, translate, and we want to go forwards. So we want to go in the position we're looking. So that's just vector 3 forward, and you want to times that by how much you want to move. So let's just say 0.1 times, and we want to say time delta time. What time delta time does is look at how fast your computer's running this simulation or game, and it looks at your frame count basically, and then it works out like a standard value, so that if you go and run it on another computer, it will have a slightly different delta time. And then it's like a scalar in this equation, so that if you times a number by that, so you're maybe moving a character or making it jump or doing some kind of action, it will mean that it will do that action at the same speed on any computer that you use, even if one of the computers is really slow, one's really fast. This time delta time just means that it's going to move by the same amount, by the same speed on any computer. So that's really handy to kind of use in lots of your simulations. So then when you change the speed, the actual speed that we want to go forward, or the amount that we want to translate, that's going to be true across all computers that you use, all devices that you want to run it on. So let's go and see if our blockhead is now chasing us, which is very scary. Let's go and have a look. Oh. Delta time is going to be a number less than 1, so it usually slows down anything. Okay, it reminds me, our blockhead, of kind of like a ghost in Mario. Oh, that'd be a really good tutorial. To have something only move towards you if you're looking at it. No, it's the opposite, isn't it? If you're looking away from it, then it can kind of move towards you. Otherwise not. So that's moving really slowly, which is kind of nice. I kind of like that. It'd be kind of like a jellyfish or a slow alien, like terrestrial fish, if that makes sense. As though it's moving through water or through the atmosphere on an alien place very, very slowly. Like it's got a lot of drag. I kind of like that. So let's quadruple how fast it was moving and go back. If this kind of works, what we then want to do is give it a physics body, because at the moment it's flying around, but maybe you wanted a truly terrestrial kind of creature like this, and I've given this guy a rigid body, and then I've moved him using physics, which means he kind of interacts with the terrain more realistically. I don't know if this guy can go through terrain. I didn't need to build that. Let's have a look if he goes straight through there. Yeah, so he goes straight through. And that's because we're not using the physics engine to move him, so he is just like a ghost. We're translating, so that's a kinematic movement. Kinematic just meaning using its position and literally just moving the position with brute force. And so that's disregarding all physics. A physics movement would be giving it a force, and then if it bumps into something, those forces would be in play, and if it was behind a wall like this, it wouldn't be able to get past. Right. But if you wanted like a ghost, then you would use a kinematic kind of movement. Rotation also is kinematic. You could add I think it's called torsion. Is it torsion? You could add a torsion force, which would rotate an object using physics as well. So the rotation we're using is kinematic rotation, and on this guy, our green mob, our green creeper, we're using a physics movement to get him. Kind of the locomotion is physics, whereas the gazing and the rotation is kinematic. Right, so let's get this guy moving using physics. So firstly, where is he? Blockhead. Firstly, let's give him a body. At the moment, all he's got is a transform his mesh, so that's what shape he is, a collider to give him kind of some physics, ready for physics, mesh renderer, so that's what it looks like, and the script that we've just created to get his rotation and movement working. So we want to add a component, and it wants to be physics and rigid body. And you'll notice by default he's given a mass of unit 1. He's got some drag. Drag is kind of like the friction or the air resistance when it moves, and gravity will be on by default. Let's just see what happens to him already. I'm expecting he'll fall to the floor and kind of roll around, I guess, as he tumbles around on the ground. Oh, there he is. Yep. So he's kind of facing down, and now he's looking up, and he's moving towards us. So that's kind of cute. He's kind of lovely. He's kind of like a little creature. Oh, looking up at his daddy. Right. There, we've kind of got stuff working. We've done it. Just added some physics rigid body, and it's already working. Let's get him to hop. So we'll leave we'll leave the kinematic movement on, but what if we wanted him to hop like we've got the other fellow doing? So what we could do is write another function, and we'll call it hop. Again, it's going to be void. We're not going to return anything. Hop. Oh, I need the body of the function. There we go. And what you can do, you can act on the rigid body itself to add a force. So we're going to say this dot get component. You didn't have to write that for the transform, because in Unity every game object will have a transform, so you don't need to kind of in a more complicated way find its other components. But this is how to find another component, like the mesh renderer, material, and all of that kind of stuff, or the rigid body. So then you write what component in these triangle arrows. I forgot what you call them. Then you want brackets, and that gets at, we've done it now, we've grabbed hold of the rigid body. And then we want dot, and we want add force. Right, and what that does, it expects a vector. It just wants to know, well, where do you want this force? And then you can times it by a scalar, and that will give you how much of a force you want to produce. So we want to hop upwards. So we're going to say vector 3 dot up, and that just gives us the vector 3 in that position. It's the same as writing 0 on the x-axis, 1, that points up on the y, and 0 on the z. So that would be vector 3 dot up is just shorthand for 0, 1, 0. And now we want to add, I don't know, something like, let's try 1. Now, we're going to hop it every single update loop. So it's not just going to do that, it's going to keep moving upwards like a rocket maybe. But will it be able to lift off the ground? Let's have a look. Did I save the script? Yes. You must save your scripts before they have any effect. Right. Okay, it's behaving in a very similar way to before. So it certainly doesn't look like it's hopping. So that amount isn't enough to begin with. And you know what, let's do this via the inspector. So we'll call it public hop force. Oh, it needs to be a float and a default value. We'll go for 10 this time, so 10 times as much, and then we want to take out 1 and just put in hop force. Let's see if he hops, let's see if he jumps. Right, he's he's struggling this time. He's kind of comedically sliding along on his ear. So presumably the force that's acting on him to make him hop is having some kind of effect. Now I've just rotated him in the right position. He's still not leaving the ground. So let's change our hop force. Blockhead, hop force 10. Let's try 100. This reminds me of times when maybe I was first learning Unity and I've maybe added a force and nothing was happening. And the reason, not that the code was wrong in the first instance, but that the amount was wrong. Okay. So that amount must have been way too much. Where is he? Oh, let's just pause the game. and look at the y value of, blockhead. Blockhead is now 7,839.68 units in the air. So every update loop, the force was definitely being applied. And what I was just saying is that you might be using add force correctly, but if you change these values a slight amount, or you have no scalar, then you're not going to have an effect, or like I've just had, an extreme effect. So we need to sort this out. Firstly, we don't want this hop to happen every update. So we need a kind of timing event. So we want to say, if time to hop, then hop. So what we want to say, we need a difference between the current time in something like seconds and the last time he hopped. And if that difference in time is big enough, then we can hop again. And then we want to reset the last time that he hopped. So if we can get the current time in seconds by using time dot real time since startup, that will give the seconds. So that will give the seconds since the game started. So or the current time in seconds. If that minus, we'll call it last hop time, is greater than, and now we want, I don't know, an amount of every 2 seconds, it's greater than 2f, then you can hop. Okay, what we also want to do, let's just use some brackets here. If we're going to hop, then we need to say last hop time equals now, which is time dot real time since startup. Okay, so we need to go and create last hop time, and that's going to be a float. Last hop time, I'm going to say is 0. So what would that mean straight away? The first time it runs, it would say, let's say the first second, 1 minus 0 is not yet greater than 2. So once 2 seconds has elapsed, or more than 2 seconds, or more than equal to 2 seconds, then he'll hop, and then the last hop time will be the current time, so then it's going to have to wait another 2 seconds before the new time minus the last hop time is greater than 2 seconds, and then it'll hop. Okay, let's see if that works. Now we're still applying the same force, but if we apply 100 force up every single loop, every update loop, then that made him take off. And I just saw him fall over the ridge. But if we just do it every 2 seconds, then maybe it's not enough to make him fly. Let's just go and have a look at him. Now I can see him kind of being jostled and moved. You can see him hopping. And it's happening every 2 seconds. There we go, there's a little hop. There's a little hop. There's a little hop. Brilliant. But it's kind of getting interrupted by which way he's kind of facing. And it's a good amount, 100. Presumably, that hop force, if we changed it to twice as much, he'll go about twice as high. Let's have a look. It also might make him move twice as erratically, which will be a problem, but we can overcome it. Okay, notice that although he's facing the ground, hop is still moving him up in the correct direction, i.e. always towards the sky, no matter which way he's kind of facing, which is kind of handy. And that's because I put in vector3.up. So whatever position you are, it uses world space. It's not relative to the creature itself. That might be handy. You could do it relative to the creature itself by writing this dot transform dot up, then it'll be relative to the creature itself. So that's a much better amount. I quite like that. It's about twice as much as it was before. But let's do something to stop it, rolling over all over the place. And that's something I've done for this mob here. He's not falling over, even though he's kind of elongated and more complicated. Even if I jump into him, kind of knock him around, he gets spun around, but he doesn't fall over. And whereas this guy, I haven't touched him, but he's got into some trouble. He's kind of, I think if I spawned these, they would have to spawn in this kind of icy tundra biome. He looks kind of camouflaged over here. That kind of suits him. Right, anyway, digressions. Let's sort him out in terms of tumbling over and things. So what you can do is find his rigid body, and then down at the bottom are some constraints. Constraints just mean stop something happening. So I can freeze the rotation on, I don't want to stop it in the Y direction because that's looking around like that, but I could stop it in the other directions. So now he can just rotate on the Y. So that means he can still follow me, but he's not rolling over and things like this. You could do this in the code. You could also say, if you notice that he's rotated too much, then you could adjust him back and things like that, which would be much more sophisticated because then it would look up and down and around and things. And you'd want to use Euler angles to do that. But I think I'm going to stop this tutorial here because I've shown you how this guy works, and we've made him instantaneously look at you, or we've used lerp to make him more slowly look at you. We've created this guy. We've made his facial features child objects of the parent object, and then we've moved him kinematically using translate, and then we've added a rigid body to move him around using add force. So you could just add force forwards to make him move with the physics instead of kinematically. So thank you very much. Thanks for watching. Goodbye.